So let's get started. The first session of the final day. Speaker is Brian Swingle from Brandeis, and he will tell us about the quantum gravity in the lab. Please start.
Great. Thanks, Masanori. Thank you all for the invitation, for coming out. Happy to be here. And yeah, I think this talk is going to be my attempt to keep with what I saw as the spirit of this conference about sort of non-perturbative methods in quantum gravity. And one component of what you've heard about so far are sort of numerical approaches. And in some sense, this is like the analog of that, where instead of using a classical computer, we're going to use a quantum computer. This will enable us to answer questions, or if you like, simulate experiments that would be difficult to do otherwise. And the hope is that we can learn something interesting about quantum gravity in this process. Okay. That's the basic theme I want to convey to you today. And of course, I'm absolutely welcome your questions at any point. Just interrupt me, or whatever your procedure is. And I'll also mention that this work supported by several different sources, it from Qubit, Air Force, Department of Energy, and National Science Foundation. So yeah, let me start. So here's the outline. As I said, the broad theme is essentially holography meets quantum simulation. I don't want to claim this is the only thing that you want to talk about in the context of quantum gravity in the lab, but that's what I'll focus on here. And the plan is to tell you, to sort of briefly survey 3 quick stories from this emerging field. It's still a very young field. I think it was, reasonably clear to many people following ADS-CFT and the rise of quantum computation that this is something that would be possible in principle in the long term. But nevertheless, not that many people have devoted time to really thinking through what's possible, what's interesting, how would you do things in a good way, and so on and so forth. Okay, so I'm going to try to give you just a flavor of some of the questions that we're starting to tackle in this area. The first point I'll talk about is quantum gravity as a source of surprising phenomenon. So this is the idea that there may be experiments you could carry out in your low energy physics lab, your tabletop physics lab, which give you an answer that you would not have guessed unless you had some kind of intuition or understanding coming from quantum gravity. And this is, can be viewed as sort of a precursor to doing experiments that are really probing what you might call a quantum gravitational effect. The reason why you need this kind of path is because the kinds of models that, we would probably all agree really display quantum gravitational phenomenon, N equals 4 super Yang-Mills or something like that, or even something as simple as SYK, are already quite complicated to implement in quantum computers and quantum simulators. So we're not there yet. We may not be there for some time. And so there's an interesting question about what things can we do first that are still related to quantum gravity, but maybe not exactly the same thing as it. And also longer term, what questions would we ask these quantum simulators to learn about quantum gravity? You don't just want to turn it on and run it or something. You want to really have a smart question to ask and answer that will complement your analytical techniques, your other computational tools, and really teach you about the theory. The second thing I'll talk about is progress towards efficient algorithms. So as I said, these models that we know of that have quantum gravity description in the holographic sense are typically quite elaborate. They involve, large N-gauge theories or all-to-all coupled fermion systems, all kinds of different ingredients, symmetries, etc. And all of these things are actually not straightforward to implement on a quantum device, or the natural language is qubits. I mean, just the simulation of quantum field theory, even a simple 5-4 theory is not straightforward. And trying to include non-abelian gauge degrees of freedom, etc., is even more complicated. And so in this context, I'll talk about a model that we defined called the Sparse Sachdev-Ye-Kitaev model, SYK model, which has a much more efficient algorithm for its quantum simulation. So if you're going to actually study the SYK model or something like that, in the lab, probably the first thing it'll do is actually this sparse model because it's vastly easier to simulate. And then at the last part, I'll talk a little bit about going beyond ADS space, IISER space, and trying to think about how you might simulate quantum cosmology. This will still be sort of within the context of ADS-CFT, where we consider an interesting kind of quantum state that has a cosmological description. But there are, broader and deep questions here about how to formulate holography in, flat space or de Sitter space, other kinds of space-times, which we don't know the answer to yet. So I just want to convey to you with this outline that there's a range of questions you can ask, from what phenomena should I be studying, to how can I study them in an efficient way, to, how do I even in principle study them? Okay, and these are all interesting and all part of this program. So that's the plan. So now let me address, what is quantum gravity in a lab? And I'll start out just by being totally honest. We don't really know. We're not sure what all we want to mean by this phrase. I think that's a fair statement. At least I don't know. Certainly, we hope, at least I hope, that we can one day experimentally probe the quantum mechanics of the sort of naturally occurring gravitational field, the field that holds us down to this planet and makes the stars move around and so on and so forth. But I think, or at least I'll argue, that we'd also like to include experiments with engineered quantum systems which have an emergent gravitational description. So think, SYK model or a holographic field theory where there's a dual description in terms of gravity. I think we'd also like to call that quantum gravity in a lab if we had built such a system. And indeed we can. And, and it's not clear what else we want to include here, if anything. A vague guiding principle that I kind of like, I don't, again, claim this is the final answer, but, sort of what we're looking for are systems where there's some simple description, either a direct, obvious description in terms of the natural variables that we see around us, or some kind of emergent description, as in the ADS-CFT correspondence, some kind of description of the system in which the description is simple and involves quantum space-time geometry. This is very likely the case for our own universe, although we have not directly observed quantum effects in the gravitational field. But it can also be true, as I just emphasized, for tabletop experiments. You could build a system in your lab for which the simplest description of the physics of that system is a quantum fluctuating gravitational field. Maybe not exactly of the kind that we have in our own universe, but that's fine. It's still an interesting system. It's still a piece of physics we want to understand. And I want to note that there may be other conditions we want to demand. For example, the presence of black holes, or topology change, or whatever the thing it is that you want to understand about quantum gravity. But that's something to keep in mind. So I just want to kind of pause here and celebrate for a moment the fact that this is possible. It's really a combination, in my view, of two very deep ideas about the universe. The first is holographic duality, which many of you, I'm sure, are familiar with. The idea that we can have a quantum field theory or some kind of quantum many-body system, which is exactly equivalent to a theory of quantum gravity in some kind of universe, an anti-de-Sitter universe, for example. And with this idea, we combine with the idea that quantum computers should be able to simulate any naturally occurring phenomenon, but at least quantum field theories, for example, which are just complicated quantum many-body systems with an infinite number of degrees of freedom per unit volume. So we put an IR cutoff, we put a UV cutoff, we regulate all the Hilbert spaces, and in principle, we should be able to simulate the physics of, whatever your favorite field theory is, to some precision with a finite amount of resources. That seems reasonable. So and the fact that this is really possible and something that we think we can actually construct and do on this planet is, is an amazing thought. And it's the combination of these two amazing thoughts which really indicates that we can do this kind of experimental simulation of quantum gravity that I have in mind here. We can really build a system that's holographically dual to a full quantum gravity theory, and we can experimentally probe that system or simulate those experiments on a quantum device.
So here you specifically say universal quantum computer just because probably analog simulator approach is hard for realistic or more interesting system?
That's probably true. The question was why I say universal quantum computer as opposed to analog simulator. And yeah, I agree that analog is probably not going to get you all the way there. But I don't really want to exclude that. I mean, I'm happy to include that as part of the story. I just use that as a sort of simple catch-all. So I think this is really amazing. And like I said, once you appreciate these two facts, it's reasonably clear that you can simulate quantum gravity in your quantum device in this holographic sense. But okay, that's a great sort of, opening thought, but there are still many questions as I outlined before. Okay. So for this talk, as I said, I'm going to stick to this relatively narrow sense of quantum gravity in the lab. Necessarily involves holography. The boundary, the CFT and ADS CFT is the thing we sort of construct in the lab. The bulk, the gravitational description, is the immersion thing that we're trying to learn about or probe or simulate. It's not directly related to the gravity that holds us down and moves the planets. But of course, we would hope that we learn some lessons that are more generally applicable, lessons about black hole dynamics, for example. So in this narrow sense, I want to note that there are things, investigations that don't qualify, despite involving quantum and gravity in labs. So for example, analog simulations of Hawking radiation are not fitting the bill as I outlined them here. And I just want to emphasize that I'm not saying these are not interesting. They are, I think. But it's just not what I'm talking about here. Okay. So any questions about the setup or motivation before I start to tell you these stories? Okay. So the first thing I'm going to tell you about is a paper that I wrote with a whole bunch of people. I guess actually in 2019 now. Wow, that was a long time ago. It's been a long year. With all these folks. And a second paper is going to come out soon, probably January 29th, in coordination with some independent work from the group of Norman Yao. And yeah, the title of this paper is actually Quantum Gravity in the Lab. And I'm going to explain one of the key things we were talking about there. So here the idea is, let's look at this quantum circuit. This is a quantum circuit that you can hand to your experimentalist friend, or that you can program into an IBM quantum computer or a Google quantum computer or whatever, and you can run it and see what the outcome is. And this quantum circuit is going to, is inspired by a quantum gravity experiment, but you don't need to know anything about quantum gravity to run this circuit and to see something surprising. So let me explain what's going on here. So the idea is we have some Hamiltonian. This is denoted H right and H left. There's two copies of the system, the left and the right copy. And at the initial moment, the system is initialized in a so-called thermal field double state. So this is an entangled state of two systems, the left and the right system, such that if you trace out the right or trace out the left, it looks like a thermal state on the remainder. So it's a pure state, an entangled pure state that is like the minimal bath, the minimal heat bath that would produce a thermal state on one side of the system, on the left or the right side. And we are going to imagine that this thermal field double state, which is between the left and the right sides, the left side is divided into A left and B left. Those are two subsystems. Maybe A left is going to be small, like a probe system. And the right is also divided into B right and A right. And the first thing we're going to do, let's focus on this so-called straight state transfer case. First thing we're going to do is we're going to evolve on the left with the left Hamiltonian, but backwards in time. We're going to evolve forward for time minus TL. So that's why there's a plus sign here. Then what we're going to do is we're going to take that qubits in A left and throw them away and inject some new qubits called psi n in some state, psi n, these new qubits here. Then we're going to evolve forward in time by the same amount as before. Then we're going to weakly couple the left and the right via this coupling V. Okay, so here's the form of V over here. Let me move the pictures of the heads so I can point. So here's what the V coupling is. We have some carrier qubits. It could be most of them. Let's suppose M is the size of AL and N is the total number of qubits. Then we just take all the qubits in BL, of which there are N minus M of them, and we sum over all those qubits with this left-right coupling where we take poly Z matrix on the left, poly Z matrix on the right, and couple. And note there's a 1/n normalization here. So each individual coupling between, say, qubit 1 on the left and qubit 1 on the right is weak. It's a 1/n suppressed coupling. But we're summing over all of these carrier qubits, which, you know, is a sizable fraction of all the total number of qubits. And we have this coupling little g, which we can modulate to tune how strongly we're applying this unitary. And then on the right side, we go forward in time again for an additional amount of time tr, which will turn out to be, if we make it the same as t left. And what you can do this experiment. You can plug in some state here. And in the right situation, what you'll find is the state that you plugged in this input can, under the right conditions with high fidelity, emerge on the output up to a known unitary transformation. So for example, if you could think of a chaotic Hamiltonian, whatever your favorite chaotic Hamiltonian is, like the SYK Hamiltonian, go to infinite temperature. So this is just a bunch of bell pairs. Evolve for a very long time, say longer than the scrambling time, longer than the entropy time, you know, some amount of time, which is pretty long. You inject 1 qubit here. You take 2 Majoranas and you make 1 qubit. You inject a fresh qubit. You go forward in time. You do this weak coupling. You evolve again. And if this coupling is exactly equal to pi, then the state you'll get out here is exactly the same with no loss of fidelity as the input state. So what you're doing is really, you're throwing some information into this chaotic system. You're scrambling it up. You're making some kind of special weak coupling. Then you're scrambling some more. And lo and behold, it pops out again at the end of the day in a perfectly recognizable form.
So here, this is specific, you say the special coupling, but it's this is specific one is important, or?
Some properties of it are important. You can do various other kinds of couplings and it will still have the same effect. The important things are that it's, well, some of the important things are that it's weak, it's 1/n suppressed. All the terms commute is a nice feature. But
it does not have to be strictly power matrix or whatever.
Yeah, you can do lots of different things. You'll see a little bit later what the physics of this is. Okay, so that's an experiment you can do, and it's surprising. You know, you throw something into a strongly interacting system, you scramble it up, you scramble some more, and it comes out again in a recognizable form. That's a very unusual phenomenon. The inspiration, of course, comes from traversable wormholes in ADS-CFT. There, the thermal field double description is of in the bulk is you have the left and the right on the boundaries, and the bulk geometry is this eternal black hole geometry where there's actually a wormhole that connects left and the right in the bulk. And the idea is if you insert a message, say, which is like injecting this information in the distant past, that's why we go to the past first. We go to the past, we inject the information. If you don't do any coupling, this information falls into the black hole, crosses the horizon, and eventually hits the singularity. But as Gauge-Ferris and Wall taught us, and as elaborated on by many others, if you, at say time 0, make collective coupling between the two sides, you can inject some negative energy, which has the effect of essentially kicking this message back outside the horizon on the right. So it kind of gets, it's like the opposite of a Shapiro time delay. You get a Shapiro time advance, it comes back outside the horizon, and then the message can be received on the right side at some future time. So you see, I hope, all the ingredients of that seemingly random looking circuit that I showed you before. We have the backwards in time, then we go forwards, then we do the coupling, then we go forwards again, and lo and behold, the message comes out. And what I want to emphasize is this quantum circuit that I showed you here is, you know, depending on the temperature, the Hamiltonian, the coupling, etc., it really probes a whole family of phenomenon. And only some of those have a simple bulk description. You know, in case the Hamiltonian is a holographic Hamiltonian and the thermal field double is at low temperature and you do everything just right, etc. But nevertheless, the quantum gravity setup was an inspiration for this experiment, which you can then do for other kinds of non-quantum gravitational systems and see something surprising and maybe learn about those systems. And then longer term, once you actually have something in your lab that really is like quantum gravity, you can first say verify this physics and then explore how, say, stringy corrections modify this picture. Corrections that would otherwise be very hard to compute using your analytical technology.
So Brian, I understand the parallel to the gravitational system, but it doesn't seem like there's anything intrinsically gravitational about your original circuit. Couldn't I imagine a field theory problem with the same features?
That's right, you can.
Okay.
Yeah, so what I want to say is considering, thinking about this circuit is not, I don't think you necessarily would have thought about this circuit unless you had thought about traversal wormholes first. But once you have this abstraction, then indeed you can apply it. You can consider its physics in whatever situation you want.
Right, okay, yeah, thanks.
So yeah, so I'm just trying to convey here that there's, in the near term, there's quantum gravity inspired experiments, even if you're not really studying what we would, I think, all agree is quantum gravity. And, in the longer term, then you can hope to actually learn something about a system you really think of as quantum gravity, finite end corrections, stringy corrections, etc., using this setup or some other kind of setup. So let me just kind of quickly explain.
Can I say, intuitively in the previous one, in your previous page, in the gravity side, intuitively you throw negative energy, so horizon move, and the message itself is going straight.
That's right.
So in this picture, it's like a message is, coming back. But so more intuitive picture is a message is going straight, but the horizon moves, and so you can see the message.
Yeah, I mean, right. Essentially, what this is a shock wave, and it's just giving you you're gluing these geometries, but with a relative time shift in the null direction, right? So everything's kind of moving straight as it can, or otherwise, but you have this time shift across.
Can I have a quick question? Maybe I'm sort of jumping ahead. Are there models like this which would be in the usual holographic framework, have duals which are real gravitons, as opposed to lower dimensional model where there are still interesting quantum gravity effects, but no real gravitons? Or does it really make a difference?
Well, I won't say gravitons don't make a difference, but this basic physics, yeah, should still be present even in a higher dimensional gravity model.
Yeah, that I understand. Yeah. Okay. Now I was just curious to know that if I go 2 more dimensions, instead of doing a circuit analog of that in some quantum field theory in, say, 3 dimensions or something like that, then you would start having graviton. I mean, the emergent degrees of freedom would really have a gravitational wave kind of behavior. And whether that's something which can be probable in the kind of things you're talking about.
Yes. Yeah, I think the answer is yes. I mean, it's harder to control analytically these things to construct the solutions.
Sure.
But at the level of the solutions and the shock waves, it seems to all make sense, even in for ADS5, say, or whatever your favorite theory is. But then there are other questions like whether the scattering of this negative energy and the message, can that cause some decoherence, or can it scatter the message in any way? So there become questions about, once you have bulk degrees of freedom that are really effectively local, that can scatter off of this thing, you need to think carefully about what those are and how they affect the message, and that hasn't been done. But in principle, this level of the story, I think definitely still makes sense.
Sure. Thank you.
Yep. So what we would like to do is have some kind of framework in this quantum information language that includes this case, or allows us to interpret this holographic case, but as a more general framework, because then we can use that framework and we can think about a variety of models and ask, how close or far are they from the holographic setting? And that's one of the things we'd love to learn about. Our knowledge of ADS-CFT is, either bottom up or constrained to special top-down models that we can solve because of supersymmetry, etc. But maybe the space of holographic models is much larger. We just don't have control. So perhaps we could search in some intelligent way over models. And then we'd like to have some model independent criterion for, say, traversable wormholes. So here's what we've been thinking about in that context. It's called size winding. Let me explain size winding by explaining the difference between operating on the left and the right of this setup. So I'm just going to think of everything at time 0 for simplicity. You need to have the large time boost to really see this signal, but let's just, for the simplicity of diagrams, think about time 0. So I have my thermal field double, which is made of bell pairs. That's what this little lower V shape indicates. It's 2 systems left and right sharing bell pairs. And if I take that bell pair system and I apply on the right, say, the square root of the thermal density matrix, that state will be proportional to the thermal field double state. So that's one way to represent this quantum state. It's square root because you need the square root of the probabilities in the pure state so that when you trace out one side, you get the density matrix itself. And if I act with O left, some operator O on the left, and I take its transpose, then this is equivalent, according to usual rules of bell pairs, to acting with the same operator on the right, where I essentially just pass it through the bell pairs, and it's just exactly equal. It's the same operator up to a transpose, but now acting on the right. And so in particular, if I act with this operator on the left, I can pass it through to the right, and it occurs kind of before the insertion of square root of rho on the right system. And I can compare this to what happens if I act with the operator directly on the right. Then I just apply O to the right, but now it's occurring after the insertion of this square root of O. And if O is Hermitian, square root of rho is also Hermitian, then the product of square root of rho and O is not necessarily Hermitian, but it is the property that this operator here, square root of rho O, is the dagger of O square root of rho. So this and this just differ by a dagger on the right. That's what I've written in equations here. And so what we thought about is, well, let's think about expanding this operator, square root of rho times O, which is generically non-Hermitian, in a basis of polystrings. So you just have a bunch of qubits. You have a basis for the set of all operators where you just specify whether each qubit is identity, poly X, poly Y, or poly Z. That's 4 to the n operators, which is indeed the right number of basis states for the operator space. And we can expand this operator in that poly basis. It's an orthogonal basis with an appropriate inner product. And this is maybe something you're familiar with in the context of operator dynamics, in the context of out-of-time order correlators, or that sort of story. But the difference here is because this is non-Hermitian, these coefficients CP don't have to be real. They can actually be complex. And what we suggested is that there is an ansatz, which we call perfect size winding, where the coefficients in this expansion, as a function of the polystring, are real numbers, R sub p, times a phase factor. This is the only place that the complex numbers enter, times a phase factor, which just depends on the size of the polystring P. So this P with a bar around it means the number of non-identity operators in this string. So if I have 3 qubits and I'm considering the string XX identity, then this absolute value of P is 2. And so the size winding is essentially that you have a phase which winds, which increases as you increase the weight of the polystring. Okay. And why is this special? Well, if we look then at the action of this operator, O left and O right, on the thermal field double, because it just differs by a conjugation on the right, it means that from the left point of view, the action has the winding phase, but with a plus sign. And on the right, the action has the winding phase with a minus sign. And now we can see the importance of this coupling V, because when you take V and you act it on one of these poly states, this is just the thermal field double with a poly string applied to it. That's a sort of basis of states. When you act with this coupling on that basis, what you find is that it has, again, this winding form here with a winding which is dependent on G, the coupling, and the weight of the poly, and normalized by 1 over n. So you can see if there were some alpha of which this is the expansion of the operator, if you have this perfect size winding, then by choosing G correlated with alpha, proportional to alpha in fact, you can exactly unwind this left operator and then negatively wind it to get the right operator. And therefore, the action operator would just pass smoothly through from the left to the right. And I'm not going to go into it here. There's a whole interpretation where we use the fact that operator size is related to momentum in simple low-dimensional theories of gravity, momentum in the bulk. And so we can actually make contact with the picture that I talked about here in terms of perfect size winding. So I'm not going to really get into that. I just want to convey that this is a notion that you can talk about for any quantum system formulated in terms of qubits, which can explain how you can get perfect transmission in some special cases. But is more general and doesn't require that restriction. So we can talk about this for general theories, and maybe it gives us a sense of how to interpolate away from holographic models to see how stringy corrections maybe modify this perfect size winding, for example, if that's really indeed what's going on in some holographic system. And we also did a calculation in SYK. This is really the work of Sepper Nizami and Henry Lin, which shows this size winding at low temperature. There's also a work of Gao and Jafaris that I'd point out to you, where they also study this traversability problem in the context of SYK. So in other words, there's different regimes. That's the takeaway. There are regimes where this teleportation works, like you can send, for example, 1 qubit with any chaotic system, as long as you go to a very late time and high temperature. That works very generically, and it doesn't have anything particularly to do with traversable wormholes in the semi-classical sense of gravity. And then there are maybe systems where you have this size winding, some kind of damped size winding, or maybe even perfect size winding, where you can teleport many qubits in the right regime. And that perhaps has a more holographic interpretation. Okay. So the takeaway here is that we have this quantum gravity inspired experiment, which reproduces really something we really call quantum gravity phenomenology in some limit. And we have a framework for thinking about the physics of that experiment more broadly. And so then we can go into the lab and we can learn about, how, if you turn on the deformation to SYK, say how this size winding is lost. And maybe that gives us a clue about, how the bulk is modified and, by quantum corrections or stringy corrections or so forth. That's the dream.
So this size winding, it's a property you can check when operator and the state and the Hamiltonian are given. When operator and the state are given, you can talk about this property.
That's right. That's right. So this would be a property that you see. It depends on temperature. Mm-hmm. It certainly depends on the dynamics.
Okay. The dynamics is also there.
We want to apply this to some late time operator. So it depends on temperature and dynamics for sure. And
so if you have some quantum theory which has a good gravitational dual, and take a state which have a good gravitational dual, and consider a natural operator which has a good dual gravity interpretation, then you see perfect size winding.
That's the idea, yeah. Okay. So that's an example of the kind of questions or experiments you could think about doing. I'm not saying this is the only one or the most interesting one, but it's what we've been thinking about. There are a lot of other questions, thermodynamics even, just understanding one of our incorrections to black hole entropy. This is all very interesting and something you could do with a quantum device in principle. But now I want to talk about, suppose you wanted to actually implement this. How would you make a quantum computer exhibit this physics? So suppose you weren't interested in doing the SYK model. This is work that I did last year now with Sheng Long, who's a junior faculty at Texas A&M, Yuan Su, a grad student who's now a postdoc at Caltech, and Lenny Susskind, who you all know, I'm sure. So here's the SYK model. I've talked about it, but let me actually show you the model. I'm not going to use any real property of it, I'll just flash it here. There are Majorana fermions, real fermions, n of them, and you have a even integer q, and you consider sums of all possible q body terms in the Hamiltonian with some randomness and a certain normalization. And this model is interesting because if q is 4, say, then at low temperature, it has a sector of the model which is equivalent to a simple theory of gravity, JT gravity. So it's attracted a lot of attention because it's a totally concrete microscopic quantum mechanical model that has some kind of gravitational description in the right regime. And so you can ask, what if I just want to quantum simulate full SYK? Well, the earliest work was by Garcia Alvarez and all, and they just tried to direct trotterization and found that it's extremely expensive. So the cost, the number of gates to evolve for time t, is scaling at the 10th power of the number of fermions, the time squared, and the precision epsilon in the denominator. That's a very unfavorable scaling. So if you wanted to do, you know, even 100 fermions, which is barely more than we can do by brute force numerical simulation, you know, you'd need 10 to the 20 gates, which is a lot of gates, considering that we can barely do 10 or 100 gates right now. Okay, so this is sort of extremely prohibitive. And, you know, I'm not saying that, you know, these people were really just pointing out that this is something you could in principle do, and that's interesting. But you can work harder, use some technology from quantum simulation and get a better result using something called qubitization. Babish, Berry, and Nevin showed that you could simulate fully connected model in a time which scales with a number of gates which scales like n to the 7/2 power. That's a lot better than n to the 10. Still not great, but it's better. And it's also linear in time, which is nice. At this point, I'll mention, you know, that these are all sort of digital simulations. You could also try analog simulation. This is something that our distinguished chair has worked on. There's also a nice proposal from folks at University of British Columbia and many other ideas floating around. And these are all interesting. What I want to tell you is that if you modify the model somewhat, you can actually do a lot better. So we cooked up this thing which we call Sparse SYK, which is defined essentially by looking at all these bunch of terms. Here I'm considering the q equals 4 example, and going term by term and just deleting some of the terms with some probability. So with probability p, we keep a given term, a, b, c, d, and with probability 1 minus p, we just delete it. Okay, and so by adjusting this probability but making it small, we could keep a relatively small number of terms. We need to rescale the size of the variance of the coupling, so the Hamiltonian is still extensive, but we do that rescaling in a natural way. And you get this modified Hamiltonian that depends on a parameter p. And if p is a half, you've kept you kept half the terms on average, and that model is essentially the same as SYK.
So you can show it has a holographic dual, Brian?
Yeah, it still has a holographic dual, that's right. But what we're interested in here is, what if you delete almost all of the terms? What if you delete almost all of the terms so that there's only about order n terms left, where n is the number of fermions?
The dual interpretation is the same as the original one or different dual?
You mean for if
p is not the 0?
If p is like if p is a non-vanishing in the infinite n limit, then yes, it's just manifestly the same. There's the 1/n expansion is the same at the leading order. So there can be subleading corrections, but that are different, but the leading order it's the same. In fact, if p, well, anyways, so what I want to consider instead is this situation where p is chosen in such a way that the number of terms is proportional to n, with a coefficient of proportionality k that does not depend on n. So this is more like a spin chain where the number of terms in the Hamiltonian is proportional to the number of degrees of freedom. And so this is what I said before, the fully connected limit is n goes to infinity with k going like n cubed. The sparse limit is n to infinity with k fixed. If k scales with n in any way, then there's a 1/k expansion for this model. And you can show that if k is scaling with n in any way, then the leading contributions again are just the Mellon diagrams. But if k is fixed, that's not true anymore. So there are new diagrams that appear, and it's not clear what the fate of this model is. But one nice feature is that once you have this k, you can take this n to the 7/2 result and improve it to n squared times something which depends on k. Okay, and so in particular, if say with k equals 1 or k equals 2, you could still have gravitational physics, then this would be a much more efficient simulation than even this state-of-the-art qubitization simulation of full SYK. In fact, we generalize their result to the case where you have arbitrary q, in which case it scales like a high power of n that depends on q. And for any q, actually, you still get the same formula. Okay, so there's a very dramatic simplification at larger Q. And so, for example, you may have heard about these models where you scale Q with n, these double-scaled SYK models. Those would normally take super polynomial resources to simulate on a quantum computer and would basically be prohibitive. But you can simulate the sparse version of those actually still efficiently because it's just polynomial in n. So it kind of actually opens up a new regime that you can access in the simulation that you just couldn't even get at before. And the reason why it's n squared here is because you have fermions. You have to do like some kind of encoding of fermions into qubits, which is slightly non-local. And for the encoding that we used so far, you would get an n squared factor instead of just n, which would be the best you could expect. There's also another way to do it using what are called product formulas. These are basically high order approximations to Trotter series, and in which you can get sort of very, very close to linear in n, which again is the best you could do. Okay, so I'm not claiming this is the final story here. You can definitely work a little bit harder, but by considering these sparse models, you can get much closer to the best possible circuit complexity you could hope for simulation. And a reduction of 1,000 gates require, or 1,000 times reduction in the number of gates per time step is a huge reduction. So instead of needing 10 million quantum gates per time step, now you only need 100,000 or 10,000, which is again still not what we can do now, but much, much closer. And the main contribution of our paper, technical contribution, was arguing that you still have gravity even in the sparse limit. That's quite surprising, perhaps, but it's true. I'm going to skip the discussion of this in detail, but the basic idea is you have the same kind of path integral description. You can consider replicated path integral for the SYK partition function, or n powers of it, averaged over the disorder, over the J couplings, but with some fixed pattern of sparseness. You can introduce your Lagrange multiplier fields and your Green's functions, but now you have one for each site because the fermions are all distinct. They're not just entering as one big collective field. You can study the saddle points of this action, and because you don't have this large N uniformity between all the points, the saddle point's not the whole answer anymore, but it's the starting point. So you can look for a saddle point, you can find a saddle point, certain class of saddle point still has the same form as the fully connected case. And then you can analyze the fluctuations around that saddle point. And basically what you're looking for here is to make sure that there's only one soft mode, that's the gravity mode at low temperature, and all the other modes are gapped. And then it leads to quadratic order and fluctuations. You're recovering the same physics you had before, where you have this one soft mode, the Schwarzian mode, the gravity mode, and the other modes are gapped. So while it's not a full proof, because we can't analyze all orders in perturbation theory, it's at least consistent with what we see in the numerics. So anyways, there's an analysis there. There's some interesting graph theory involving the spectrum of SYK and the spectrum of these random regular graphs. It's a fascinating story, but I don't have time to tell you about it. The conclusion is just that indeed we find that only the gravity mode is soft at low temperature. And all the other modes are gapped, provided this coupling matrix, the sparseness which defines the Hamiltonian, has a certain nice property that it's essentially an expander graph.
Maybe Danger want to ask a question.
Yeah, no,
Yeah,
I'm surprised that there isn't a lower critical value of P that where the physics change.
Yeah, you know, there are definitely many questions here, but it seems that like even for say, like for example, we don't know the critical value of K below which you lose this. It certainly can't be smaller than 1 over Q, because then the number of terms is not enough to connect all the fermions. Like you'd have disconnected clusters. But it seems, you know, for say K equals 2 or 4 and Q equals 4, that you're very strongly within the gravity regime still, as far as we can tell. But okay. it's you know, I emphasize we have not fully understood what's going on here.
Yeah, it reminds you of some sort of fermionic percolation problem. You would have expected a critical PC or something like that. Is that what you were thinking, Denjo?
Exactly, yeah.
Yeah, so I think there's a critical, like, a critical K probably, which we don't know exactly, but there is a critical K above which we expect that you still have the gravity physics. And the basic physical picture is that the gravity comes from a certain pattern of symmetry breaking, from pattern of spontaneous and explicit symmetry breaking. And that symmetry breaking just continues to occur, essentially. So in the same way you can take an Ising model, an all-to-all coupled Ising model, which has a mean field like Ising transition, and then you can sparsify that, and it actually still has a transition, but maybe at a different coupling or a different temperature. It still breaks the symmetry. We think, like, that's my physical picture of what's going on here, is that if you have a strong enough coupling, it doesn't need to be scaling with n, but if you have enough of these, if you have a big enough k, then you indeed have this symmetry breaking at low temperature. And one of the nice things is we can actually do numerics. So for example, we can study this q equals 8 model with 52 fermions, which is far beyond what anyone could do before. For q equals 8, it was like essentially hopeless. For example, the full model has 750 million terms in the Hamiltonian. That's a lot of terms. But the sparse model has 208 or 416, depending on whether k is 4 or 8. So it's a vast reduction in the complexity. But here in this left panel, I'm showing you the entropy as a function of temperature. The black solid line here is the infinite n mean field prediction. These overlapping blue and red line, you can just barely see here. That's n equals 52 with different k. So you can see there's almost no effective changing k. The red and blue lines are on top of each other. There is a finite n effect. You can see the green line, which is n equals 40, is a little bit lower. And we can actually include the 1 over n correction, which is known analytically at low temperature. It's a 1 over n times log beta j form with a certain precise prefactor. And when we actually plot the data, that's this blue line here, and compare it to this 1 over n correction, it's like the slope perfectly matches. So we really have, I think, pretty strong evidence from numerics, which are actually also easier because of sparsity, that we have the gravity physics at low temperature.
Even if you forget about quantum computation and just use it as a tool to study the holography on classical computer, is it already big gain? I don't really think anybody using original SYK, for example, nobody could really see, say, the Laplace exponent equals to 2 pi t. Nobody really could see, because calculation is hard. And
that's right.
Even for that direction.
Yeah, that's right. So it does help with this, and if you want to do the largest possible scale simulation, you should use the sparse model, I think. Like when we were finishing this paper, n equals 52 was the biggest study to date. Like the previous best was n equals 44. After or around the same time we wrote this, Norm Yal's group had a study where they went up to 60 with a few samples. But this took like years of computer time, where the calculations you can do on your laptop. Okay, so it's just, and they can only do q equals 4. They couldn't do q equals 8. That would be impossible at 52 or 60. So it really is a lot faster. And so, yeah, I think it's also interesting because it maybe opens up some new avenues. For example, because you have this tree-like structure in the interactions, maybe you can do a tensor network approach, which sometimes makes sense on trees. So there may be even new ways of attacking this physics numerically, classically, opened up by this sparsity. Okay. So I gave you a flavor of the kind of questions you might want to ask. I told you about how there's interesting questions in terms of what models to use, how to simulate them efficiently. Let me, as a final topic, quickly touch on what if you want to go beyond studying quantum gravity into de Sitter space? What if you want to study cosmology, for example? And this is going to be based on 2 papers. One I wrote with folks at UBC, Sean, Moshe, Mark, Chris, and David. And then a more recent paper from last year I wrote with, or I guess again, 2019 is 2 years ago now. I wrote with my student Stefano. And here the idea is essentially, can we do brain world cosmology microscopically in ADS-CFT? So I want to emphasize, we're not the first people by any means to think about brain world cosmology ADS-CFT. I mean, going back to the pioneering work of Raman and Lisa, Randall Sundram, they were already thinking about ADS, and there are many, many papers on this subject. Our kind of new contribution is to think about precise microstates in ADS-CFT, these so-called boundary states, which are evolved in imaginary time, to think about these precise microstates and to show that these microstates when modeled in terms of, say, an end-of-the-world brain, can actually give you gravity localization, as in Randall-Sundrum and cosmology on the brain. Okay. So this is an old topic, but we have a new ingredient, which are these microscopic constructions, completely well-defined Euclidean evolved states that actually realize this physics in a full ADS-CFT setup. Okay. So what's the idea of Randall-Sundrum? We live on a brain. The brain is coupled to gravity in a higher dimensional bulk, but because of the structure of the geometry in the brain, there are modes of the bulk gravity that are localized to the brain and which approximate ordinary GR. Okay. It's a beautiful idea, a lot of motivations for it. People look, for signs of it even in LHC. So it's a very interesting subject. And again, our point here is to say, can we realize this microscopically in a precise CFT construction where we say this state actually has the cosmological brain in it? And the idea, again, is we're going to use boundary states. This is some kind of, the nature of this state depends on the theory, but for SYK-like things where you wouldn't have a notion of cosmology, but you can still consider this kind of state, this would be like a product state in the computational basis formed by pairing up the Majoranas in some way. For CFT2, this could be like an Ishibashi state, some kind of left-right entangled state, left movers, right movers entangled. And generally it's some kind of conformal boundary state. And we're going to evolve this in imaginary time, and in ADS-CFT, this can be dual to, say, some kind of black hole space-time where there's a brain, an end-of-the-world brain, denoted by this red line here, which sits behind the horizon. So the sort of old brain world picture would be that we're like over here on this brain. We have this ADS space, maybe without a black hole, maybe with a black hole. And we're kind of thinking about this thing. So now it's all being macroscopically, holographically realized by a CFT on the other side of the black hole. So there's a CFT over here, a microscopic quantum system. And it's in some particular quantum state such that the description is there's a brain behind the horizon of this black hole from the right point of view, where you have cosmology happening. And so the idea would be, going back to our theme of simulating quantum gravity, if we can prepare this state in the lab, and there are ways to do that, then we could actually evolve it in time and maybe probe cosmology on the brain using some observables on the right side. Of course, that's challenging for a variety of reasons because it's behind the horizon, but it's in principle doable. The basic technical construction we're using here is the ADS-BCFT dictionary. Basically, the rule is in the simplest case, you have a manifold on the boundary you have the manifold on the boundary with a boundary. So there's a boundary on the boundary, and that boundary on the boundary extends into the bulk as an end-of-the-world brain. Okay, here's a picture. The NCFT is the manifold of the CFT. MADS is the ADS space-time, and it has now a boundary. The bulk has a boundary, which is the CFT, as well as the end-of-the-world brain. And we consider some combined action, which has, say, the bulk gravitational action and also some boundary action associated with end-of-the-world brain. And this would be the simplest model. It's like a constant tension brain. You could, of course, consider more elaborate models, but we stuck with this simple thing. And so what you have then is you have a CFT on a cylinder, say this, each point here is a circle or a sphere in their dimensionality. And then we have some amount of imaginary time tau naught. And we're computing the matrix element, the norm of this state, essentially, the overlap of this state here with itself. So the total amount of Euclidean evolution is 2 tau naught. So this is the bra, this is the ket. And then we need to fill in this geometry with some bulk space-time terminated by a brain. And there's essentially two possibilities in this simple model. The brain can have two disconnected pieces, one touching the forward boundary state, the future boundary state, and one touching the past, but not connected in the bulk. This is like, in this case, the bulk geometry is just ADS. And then there's another possibility where the brain connects between the past and the future, in which case the bulk geometry turns out to be that of a black hole. And this is the case we want. So essentially there's some work to do to find these Euclidean solutions and to show that this is the one that dominates in the regime of interest. Okay. This is a kind of picture of what happens. You take this this total thermal circle of total length beta. You have some horizon point at the center of the circle. So this is a Euclidean picture. You have the sub part, the length subtended just by the imagined time evolution of your boundary state. And the brain has some kind of point of closest approach to the horizon in Euclidean. And you have some region of the space-time that's cut out. That's this gray region, or sorry, that's preserved. So the white's cut out and the gray is kept. And then when you go to Lorentzian signature at, say, time 0, you have a picture where you have the CFT on the right in asymptopia, the horizon here, and then the brain is sitting at some point behind the horizon, and it will then subsequently evolve in some interesting way. In these models, it will fall into the singularity eventually. So we wanted to look for gravity localization, because that's kind of the key thing. You need to have cosmology. You need to have 4-dimensional gravity on your 4D brain, on your 3 brain living in 5D bulk. And there's some well understood criteria you can search for. Localization is not going to be perfect in this case, but we can still ask for effective localization for lots of modes of the field over a relatively long time. And there's some basic requirements: that the brain should be much bigger than the black hole size, that the Hubble constant is smaller than the inverse ADS radius, so other requirements. And we found, for whatever reason, I don't think we still don't deeply understand this, that in this simple setup here, with just this action, you couldn't actually get this. That is, you would essentially need a tension for the brain approaching 1, but the Euclidean solution stopped making sense when the tension was bigger than some value less than 1 in more than 2 dimensions. It folded back on itself in some way, and it just did not seem to give a sensible Euclidean solution. The Lorentzian solution looked fine, but the Euclidean solution didn't make sense. And so maybe we could do better if we understood like brain interactions, because it had some kind of crossing of the brain, or if we had a more complicated brain model. What Stefano and I showed, and I should mention that Mark and friends, I think, have their own improved study where they've also been able to exhibit some of this physics, but I don't think it's appeared yet. So keep an eye out for that. But with my student Stefano, we showed that actually if you change the setup slightly, if you include charge in the black hole, so you consider a charged black hole, then you can actually have brains with tension approaching 1, sensible Euclidean solutions that dominate the path integral, as long as you tune the black hole near extremality. We don't understand exactly why you need to do this, but we showed that it exists and makes sense. This is kind of what the brain looks like now. So now instead of having an ADS Schwarzschild, you have ADS Reiser-Nordstrom, and the brain is moving in principle, in this infinitely extended space-time. And if we're, say, looking here in this little patch, then the brain is executing some trajectory. I don't want to take seriously what's happening in the far future or far past. There could be some singularity structure that's different. But for this little section right here, we can work out the same kind of story as before, where this is the brain moving behind the horizon. This is the asymptotic CFT, for which it's a microstate. And we can find that this solution dominates the Euclidean path integral, has a sensible Euclidean solution, has a sensible Lorentzian analytic continuation. And we can even show that you have gravity localization in some limit. So this is just a table. I don't want you to process the details of this, but the columns are, this is the Hubble time, like the inverse Hubble constant, the oscillation time of a mode on the brain, the decay time, and you can see that the oscillations happen fast compared to the Hubble time. So essentially you have gravitational modes that are waving at some time scale short compared to the time scale of the universe, time scale of the cosmology, and they're decaying at a much slower time. Okay, so you have a right separation of scales in the right limit to have modes that are approximately localized on the brain that look like 4D gravity modes that live a long time, and all the approximations we use to give this calculation are valid. So there's some various adiabatic approximations that we used to make this study, and these other columns are showing that those approximations are very valid. Okay. So long story short, we can construct in this bottom-up model Euclidean microstates with end-of-the-world brains that host gravity localization on a brain which is executing some cosmological trajectory. Now, this cosmology is not our cosmology. We're not there yet, but it is kind of exciting to me that in principle we have this concrete, well-defined microstate in the CFT, which has in its description somewhere a essentially well-defined 4D cosmology for a long period of time. And then at the big crunch and the big bang, you realize you're actually part of a 5D universe, but okay, that's fine.
Sorry, Brian, can I just ask a question at this point? I guess I got a
Please.
bit confused. This is, I mean, the normal Randall syndrome brain is, I can think of it as like a UV cutoff. It removes the boundary portion of the bulk.
Yeah.
Now, your brain is not doing that, I think.
Well, it's doing it on one side. So let's look at this picture. So normally I would say that I have just this side here, the left side. And yes, I would say, you know, if Roman was giving this talk, he would say, okay, we have some CFT where we've deformed the UV. So this is like an infrared CFT with a UV cutoff coupled to gravity, and that's what the description of this thing is. And what I'm saying is you can think about a very similar kind of setup where you actually have a true CFT on the other side of the black hole. And this whole setup is actually just a microstate of that other CFT, but in this funny boundary state that causes there to be a termination of the space-time behind the horizon. And this description follows from just the BCFT ADS rules that you know we more or less agree with.
Yeah, and so you've got specific operators to create this microstate. I mean, you understand what this microstate looks like.
Yes, in fact, yeah, indeed we do. So I'll advertise a work. You know, we can try to get very precise about this. So Stefano and I have a paper that will nearly finished where we very carefully dimensionally reduce this 4D gravity model to get a JT gravity model. We put the brains near the horizon, and then we can actually exactly match that very precisely to microstates and like charge SYK, for example. So it really does seem to like make sense. I'm not claiming that we know exactly what the microstates look like for this full 4D gravity theory or 5D gravity theory, but for cases we can check so far, it seems to really actually make sense. Yeah, so we get localization. And so, okay, maybe we can even study cosmology using a quantum simulator one day. And so with that, I'm about out of time. So let me just wrap up here. What I hope I convinced you is that quantum gravity, you know, in the lab is a rich subject, and it's not just about trying to detect very tiny signals from gravitons or about looking for signatures of quantum fluctuations in the cosmic microwave background. Those are all extremely interesting, but it's a bigger subject than that. And I think that simulations of holographic models of gravity are going to actually come to realization much sooner than we make progress on these other topics. Okay, maybe we'll see, you know, maybe we'll see some relic fluctuations from inflation. That'd be great, but you know, seeing gravitons seems very challenging. Whereas actually these simulations, these quantum simulations, while very challenging as well, actually I think are plausible in the, you know, maybe we could simulate SYK in 10 years. I don't know. That would be pretty cool. Because there's a lot of models, even though we understand SYK, there's a lot of related models like tensor models, which we don't understand. And, you know, maybe also very nice, this synergizes really with the broader effort to understand complex, chaotic, highly entangled quantum systems. And maybe the final takeaway is I think hope I convinced you there's like many directions to think about, whether you're interested in algorithms or, you know, how to simulate cosmology or doing string theory corrections. Again, our distinguished chair, you know, they put a paper out very recently talking about simulating matrix models on quantum devices. So there's lots of work to do, and I think it's an interesting subject. And we'll one day teach us a lot about quantum gravity. We're not there yet, but actually just the process of thinking about how to do these simulations is already giving us a lot of surprises. So thank you for your attention, and happy to take further questions.
Thank you very much. So we have like 25 minutes for discussion. So we spent 5 minutes of discussion time already, but we still have 25 minutes. So you can ask as much question and comment as you like. If anybody has a question or comment.
Oh, sorry. Can I ask a question?
Yeah, go ahead.
So I might have missed part of your discussion about the sparse model.
Yes.
So so is there some limit like q going to infinity where the model is solvable?
Yeah. So yeah, there's various senses in which that's true. So I said that there's a 1/k expansion for this model.
Right.
There's also, it's really like a 1/kq expansion as far as we can tell, or maybe I don't know. There's various expansion parameters, but making q large does help. Essentially because these terms now touch more fermions, so the effective connectivity is higher.
Right.
And
I mean,
so yeah, go ahead.
In the normal case, it sort of maps into a Louisville theory, and that's sort of very useful. But in this case, maybe it becomes something even more simpler. I don't know.
I think it actually it also becomes that Liouville theory. So
I see.
the large Q gives you extra control also in the sparse model, but what that control buys you is that you just recover the fully connected limit.
Oh, I see.
That's as far as we understand at present.
Okay, thank you.
Yeah. And like another thing that we'd like to understand is doing the same kind of construction for like non-abelian gauge theory. So like take the nonlinear parts of the trace f squared, and can you like sparsify that matrix coupling? This definitely breaks the gauge symmetry, but that may be fine. At least it's strong coupling. It's not clear that that's essential. And this could be useful because if you take our usual quantum algorithms, try to simulate, say, large N QCD or something, the simulation cost for the quartic terms is quite expensive. It scales like a high power event. So it's not uniform in the same way that we'd have in a large N expansion. The different terms cost different powers of N. So there's a lot of just basic algorithmic work there to be done to understand, how better to simulate those things from a quantum algorithms point of view, and maybe also new kinds of gauge theories where we, for example, randomly break the gauge structure and see what happens.
Toby?
Yeah, I mean, this is probably a very naive question, but in your simulations of SY or the sparse SYK, are you able to think about dynamics, time dependence?
Yeah, so this right plot is the Green's function as a function of time.
I see. Sorry, I missed that. I see.
Yeah, no, I mean, it just went very fast. So the blue line is beta equals 0. This is infinite temperature. The dashed is what you would expect from the large N Schwinger-Dyson equation, or, well, the real-time Schwinger-Dyson equation. And this is the same thing at low temperature, beta equals 17. I mean, it's known that it's sort of hard to see a lot of decades of exponential decay because you have these corrections coming from the Schwartzian, the quantum Schwartzian, that are important at relatively modest times. But yeah, we do see, roughly this decay with a change in the slope. You can look at out-of-time order correlators. It just takes more time, computer time, but you can do it. The essential technique is we're taking a state and we're evolving using a Krylov technique. So we're just applying the Hamiltonian to that state many times to create a Krylov space, and then we evolve unitarily within that space and keep going. So all we need to do is have efficient matrix vector multiplication. And the time to apply a Hamiltonian scales with the number of terms. So when you have 100 million terms, it takes a long time. Whereas if you have only 200 terms, it's 1,000,000 times faster. Okay, and you can parallelize that, etc. But that's the basic technique that we're using.
I feel like you're breaking no free lunch theorem. So this huge reduction, but still you're seeing reasonable physics. Why? So does it mean original model has some unnecessary terms, or maybe?
Yeah, I think that's a fair way to say it. I mean, the physics is not identical. Of course, there are 1/k corrections to various, like you can compute.
So wait, let me check. Large N limited the same, or you see different?
No, even at large N, like suppose we look at the large N entropy density per particle. That has a 1/k correction.
Okay. Okay.
Which is non-vanishing. It's just it happens for whatever reason to be very small. Like we computed this in our paper in the high temperature expansion. We computed the leading 1/k correction. And for whatever reason, it just happens to be like a small effect, even for k equals 1 or 2. I'm not sure that there's any deep explanation for that. But then at low temperature, I think there is a deep explanation, which is the low temperature heat capacity is coming from the gravitational sector. It's coming from this symmetry breaking, and that symmetry breaking pattern is still there. So that's why the low temperature heat capacity is kind of universal. There will be corrections, but they'll probably have higher powers of temperature. So in some sense, they're like irrelevant at low temperature. We'd like to have some kind of RG description of this model where you can see that the sparsity is irrelevant in some sense, like you kind of flow to this fully coupled limit, but we don't have that yet.
Mike, you're raising hand now.
Oh yeah, I just had a quick question. You mentioned about the charged black hole and the possibly extremely charged black hole. My understanding is that there could be a non-zero amount of entropy, and at zero temperature, it has some peculiar properties. So how does that manifest in the CFT? Do you have to have like a chemical potential instead of the temperature? Or how do you represent that?
That's right. Yeah. So you need to tune the chemical potential, and so you have to have temperature and chemical potential, and you have to tune them in such a way the temperature is getting small, but the chemical potential is remaining finite, and the CFT dynamics is such that the near extremal black hole is the solution. This is certainly not obvious. I mean, if there are other fields in the bulk, they often will condense in this limit and change the geometry. So, I mean, there are, as I'm sure you know, like examples where it is robust, like you really do have this near extremal geometry, but it's not guaranteed. And, in the bottom-up model that we considered for our work here, which is just this plus a Maxwell field, we're just saying that this is the only possibility by fiat. There's no other fields that can condense. But if you had other fields, they could potentially condense and might change the story. So, yeah. So you need a special CFT with a special property and the right tuning of chemical potential for this to be like literally true for that CFT.
And this could be a place for quantum advantage in a sense, because chemical potentials are very difficult to do on classical computers, like finite density. So
exactly. Yeah, this would sort of all be very hard to do. Chemical potential, some out of equilibrium initial state, real-time evolution would all be very challenging.
Yes, that's right.
Yeah.
Okay, thanks.
Your evolution is in Euclidean time, is that correct?
Yeah, so it's initially in Euclidean time. So there's a Euclidean part, which we can then continue analytically at, say, 0 time. So like in this picture.
Right. No, but I'm really interested just in this graph you showed of this falling thing. What is the computation there? Is that a unitary evolution, or is it?
Which graph?
The rapidly falling graph you had as a function of time. It's gone. Yeah, toward the end, your results. Yeah. Somewhere. You had this comparison, green lines going down very fast, exponentially down.
Oh, sorry. That was for the sparse model.
Oh, yeah, but what? So is this is Euclidean time?
This is real time.
This is real time. Okay. And so so it's a unitary evolution, is it here?
It's a unitary evolution. That's right.
So how you seem to describe this as applying the Hamiltonian over and over again? So it's a sort of a series, or are you really doing unitary evolution?
The evolution actually is unitary, but it's unitary in a subspace. So the trick we do, so the naive thing would be to take the time evolution operator and expand it. Like if you want to evolve for a small amount of time, delta t, you make a power series expansion.
Yeah.
And you just keep the first 20 terms of that.
Yeah, sure.
A better way to do that is to take those first 20 terms, which corresponds to psi, h psi, h squared psi, etc.,
Yeah,
and form an orthonormal basis. So you do Gram-Schmidt,
sure.
and then evolve unitarily in that subspace, but do it exactly. And this is what we're doing here. So it is unitary, but it's an approximation to the
You
true
set up
dynamics.
a Krylov space and truncate on
Exactly.
that space. And
Exactly.
then evolve. So I mean, this is just a random thing, but your sparsity, of course, if you look at h squared versus h cubed and so on, of course, the theory becomes less sparse, right?
Right.
Right. So, I mean, one way to maybe think about it is that, you could think of the effective theory as being some power of h, which is then less sparse. And if that dominated your long term, then it would connect to the statement that sparsity was not the crucial element.
Yeah, I like that picture, and I would like to have a picture like that that's more quantitative. So that's all. Yeah, I share that intuition, and I think that would be nice to.
Yeah, I'm not trying to explain it. I'm just trying to say, wait. I mean, but that's what happens in any sparse problem, right? As correlation length grows, the problem in some sense becomes less sparse, right?
Yeah, indeed, right. These fermions see more and more of their friends as they go along these chains of couplings.
And we know, for example, that mean field theory kicks in at a fairly low sparsity and then is equivalent to everything attaching to everything. So there's a lot of examples of this, right?
Yeah, I agree. So yeah, I think this is someone out there wants to do this. I think it's a very concrete project.
I wasn't volunteering.
Maybe I have another question. I spent a long time thinking about brain worlds a long time ago, but it seems very odd to me that you could get a localized graviton on your brain, in the sense that your brain is in the infrared. So it looks more like an excitation of your theory, which, as you say, it is. It's a CFT in some state.
Yeah.
I see, but it's somehow important that the scale factor is decreasing and then increasing again, right? So in terms of the warping and the scale factor, the brain has to be in some sense in the UV, meaning that space-time has to be expanding towards the brain, I think, to have any chance of localizing a graviton.
That's right. Yeah. So let me be more precise. This is an important point. So yes, we need, first of all, we're going to think about this near this point of time reflection symmetry. So we're going to have the brain, which is very far away. So it's locally in this region of space-time, it's very much like the original setup. It's nearly anti-de Sitter space here. The black hole is, is far away. The brain is moving slowly. It's near its turning point. So the velocity is vanishing and there's just a quadratic term. So it's moving slowly, and for this regime here, that's where we really have approximate localization. And then once it gets close again to the horizon and penetrates inside, it's lost. So it's only for a finite amount of proper time of the brain evolution, and only if the brain is far enough away and satisfies some other conditions. It can still.
I mean, in the real case, it would extend to the boundary, which of course it isn't here because it's falling through the horizons. And I just sort of wonder whether it's just the same thing or not. I mean, I guess you've done the calculation, so it is. It's strange.
Yeah, I mean,
it looks different. It's because it's not. In some sense, it's not near the boundary.
It's certainly not near the right boundary at all, and it can
no, it's not even near the left boundary because it doesn't touch it in the same way that the usual brains do.
That's right. So essentially, like as we increase the tension towards one, it gets closer and closer to the putative left boundary, but it never gets there.
It's obvious the metric on it's cosmological just by symmetry, but I suppose the question of whether you really have a localized graviton is quite subtle.
Yeah, I think that's a fair statement. And so what we literally did, just to be totally precise, is we take this thing, we make an adiabatic approximation, so it's slowly moving and very far away, and then we use like this technology from Sierra, Clarkson, and Martins to study the spectrum, and we just find that there are modes with very small imaginary parts. So it's quasi-normal modes of this brain with very small imaginary parts. And you can see, the wave functions are sort of peak near the brain and have some tails and, all the usual sort of story. But indeed, it only happens for some finite fraction at best of the proper time of the evolution.
And that somehow controls there's some complex bit to this. These gravitons somehow decay in some sense, presumably.
That's right. So this TD here is 1 over the imaginary part, I guess, of the frequency.
Yeah.
So you can see it, for this example, it's about like 1,000 times. It oscillates 1,000 times before it decays.
Yeah.
And then also the brain itself is moving, which we're also kind of neglecting or treating in an adiabatic fashion. So that also is going on.
Thank you. Yeah.
Is there any other question or comment? If not, maybe we already had a lot of question and discussion time, so we can thank speaker again. Thank you very much for nice talk.
Thank you.
Thank you.